Significance testing for two sample proportions. So, our null hypothesis becomes P1 minus P2 equals some value. We're going to stick with the situation that the difference is 0 between these. That is, the second thing doesn't have any different effect than the first. So, in other words, the null hypothesis is that the two proportions are the same. And our alternative hypothesis could be one of three things. The difference could be greater than 0, less than 0, or equal to 0. And just like in the confidence intervals, if the random, the normal, and the independent conditions are met, we can proceed with our calculations to perform this significance test. So to do a test, we're going to standardize our difference, and we're going to get a z-score, and we're going to use that z-score to find a p-value. Our test statistic, remember, our z-score, is the statistic, the difference between the p-hats minus the parameter, so minus 0 in this case, because our null hypothesis is that the difference is 0. And then we divide by the standard deviation. If our null hypothesis is true, that is, if there's no difference between the two proportions, the two parameters are the same, and we'll call their value p. But we need a way to estimate p. We use p hat as an estimate for p1 and p2. So we're going to combine the data from the two samples. The proportions are the same. We should be able to pool everything together. We call this the combined sample proportion or the pooled sample proportion. So the way we get that, the way we get p hat sub c, the statistic for the pooled proportions, we take the two amount of successes, add them together, and divide by the two counts of the individuals in both samples. And we'll get a new value, and guess what we use that for? We use that to find our standard error. We don't know p for everything together, so we use this pooled p hat to get our standard error in this problem. So if the following conditions are met, we can proceed with a two-sample z-test for the difference between the two proportions if our data is random. So we have a sample size of n1 and a sample size of n2, and if those two things were generated randomly, we're good to go. Normal, if the counts of successes and failures in each sample group are at least 10, that is n1 p hat 1, n1 1 minus p hat 1, and same thing for the second, those at least 10, we have the normal condition met. And finally, independence, both samples or groups themselves are independent. That's important. Both the samples and the groups must be independent of each other. So population 1 and population 2 must be two independent groups. And when we are looking at each group independently, then within those groups, the sampling must be independent. And if we are sampling without replacement, this is where we look at our 10% condition. So summing this all up, suppose our conditions are met and we have our null hypothesis, the difference of proportions is 0. First we find the pooled proportion, and then we compute the z-statistic, and we are finding the p-value the same way we did with one sample z-tests. So let's do a couple examples. We're going to do this one by hand. We're going to do the next one with a calculator, and we're going to get through this and move on to means in the next section. So we want to look at a survey or a study that compares the proportions of children who come to school without eating breakfast in two low-income elementary schools. First school, SRS of 80 students, found that 19 had not eaten breakfast. School 2, SRS of 150 students, 26 had not had breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? Carry out a significance test, alpha equals 0.05, to support our answer. So, our hypothesis is that P1 minus P2 is 0. That's our null hypothesis. And what that means is that there is no difference between school 1 and school 2 for the students that don't eat breakfast. And you need to make sure you're defining P1 and P2. P1 is the proportion, at school 1 who did not eat breakfast. P2 is the proportion at school 2 who did not eat breakfast. Our alternative hypothesis is that these aren't the same, that P1 minus P2 is not 0. So our plan, we have to test our conditions. Random. Our two schools are independent of each other. And within each school, we are collecting a simple random sample from each. 80 from school 1, 150 from school 2. Normal. We're doing N1 P1, N minus 1 P1. You got these. These are all at least 10. Cool. Independent. We have two independent samples, one from school 1, one from school 2. Those schools are separate from each other. And we also have to look at the individual samples taken from each. And since we are sampling without replacement, we must check the 10% condition. So 10 times 80 is 800, and 10 times 150 is 1,500. And we are told up here that there are more than 1,500 students at each school. So we have met our three conditions. We can carry out our two-sample z-test. First, we find our pooled proportion. We add together the successes divided by the added together total number of students. We get p hat sub c equal to 0.1957. Then we calculate our test statistic. Here's our difference in the p hats, minus 0 over our standard error. We get a z-score of 1.17. We get this picture. It's two-sided. We look up 1.17. We find that p-value. It is 0.2420. Well, that's what our final would be. But 1 minus 0.8790, that's what we get when we look it up. And our p-value is 0.2420. And since our p-value is greater than the chosen significance level, we fail to reject the null hypothesis, and there is not sufficient evidence to conclude that the proportions of students at the two schools who didn't eat breakfast are different. Huzzah! On to example 2, dealing with heart attacks and whether or not a drug makes a difference. So, will using a drug to lower blood cholesterol reduce heart attacks? We are going to use volunteer subjects who are assigned at random to one of two treatments. This many men took a specific drug to reduce their cholesterol levels, and a control group took a placebo. During the next 5 years, 56 men in the drug group, the treatment group, had a heart attack, and 84 men in the placebo group had a heart attack. Is the apparent benefit of this drug statistically significant? We're going to do a test to find out. Our hypothesis is that there is no difference. Our alternative hypothesis is that P1 minus P2 is less than 0, meaning P1 is less than P2, which means that the people who took the drug had fewer heart attacks. This is where it's very important to understand what P1 and P2 mean. And in this problem, we are going to use a significance level of 0.01 because type 1 error is fairly significant in this problem. Concluding that this drug reduces heart attacks when it really doesn't, that would be kind of bad. So we'll use alpha equals 0.01. So here we go. We're going to perform a two-sample z-test if these conditions are satisfied, and whether you're using a calculator or doing this by hand, you must check these conditions. Random. Our data came from randomly selected groups. Normal. We got N1 P1, N1 minus P1, N2 P2, and that's what all these are. These are all at least 10. I get tired of saying all the P's and 2's and 1's and whatnot. You know what these are. We're used to these. Our normal condition is met, and our independence, due to the random assignment, the two groups themselves are independent. And within the observations, or within each group, the observation should be independent. And here, the 10% condition does not matter because whether we know the person next to us had a heart attack or not doesn't affect whether or not I have a heart attack. So, since we have our conditions met, we can do our two-sample z-test for the difference. Our pooled proportion, 0.0343. Our standard error is down here on the bottom. Our test statistic calculates out to be negative 2.47. Our p-value ends up being 0.0068. This is a one-sided test. And since our p-value is less than our significance level, our results are statistically significant at the 0.01 level. And what that means is we can reject the null hypothesis, and we conclude that there is convincing evidence of a lower heart attack rate for middle-aged men, like those who take this drug, compared to those who take only a placebo. So there we have it. Here's a summary of what we have looked at, but I want to jump out of this and I want to go to our calculator. So let's do this same significance test with our graphing calculator for this heart attack study. So again, we have to check our three conditions just like we would if we're doing it by hand. But now to do the actual test, we're going to go into menu statistics, down to stat tests, and we are going to do a two-proportion z-test right here. And we type in our x1, n1, x2, n2. So we have 56, 2051, number of successes, that is heart attacks. It's hard to call a heart attack a success, but there were 84 heart attacks in the second group out of 2030. And our alternative hypothesis was that P1 is less than P2. That is, there's a smaller proportion of those who took the drug that had a heart attack than compared to those who didn't take the drug. I hit OK, and we have all our data. Here's our P hat sub C. We should write that down. Here's our p-value. Here's our test statistic. We have all the same information, and we compare our p-value to our significance level of 0.01, and we still conclude that we should reject the null hypothesis. So there we have it. We are done for today, ladies and gentlemen. I hope to see you next time for studying confidence intervals and significance testing for 2z/t tests for means. That is all. I shall see you in the next section.